Okay, alkenes all have a carbon-carbon double bond in them. The simplest alkene that we have is ethylene. That's a common name for this compound, which in the IUPAC naming method would be Ethene. Eth for 2 carbons, ene saying double bond. But commonly we call this ethylene. If I look at the bonding for this molecule right here, if we analyze the bonding for this, we'll understand the bonding for all carbon-carbon double bonds. So the first thing that we're going to do is we're going to look at this Lewis dot structure up here and figure out what the hybridization is and everything. If I look at carbon, I would see there's 1, 2, 3 areas of electron density, and the same over here. So both of these carbons are sp2 hybridized. sp2 there's an sp2 orbital that bonds out here to the s on a hydrogen, and sp2 that reaches out here to bond with the s on hydrogen, and again the same thing over here, sp2 to s on hydrogen, sp2 to s on hydrogen. Now let's look at the double bond. Between the 2 carbons there will be one orbital, one bonding orbital formed by sp2 overlapping with sp2. And because it's head-on overlap, that forms a sigma bond. So I'm showing it right here for you. Notice here are the bonds to hydrogen, carbon to hydrogen. So this is the carbon, hydrogen, hydrogen. This is the carbon, hydrogen, hydrogen. And sp2 to s, sp2 to s, sp2 to s, and sp2 to s. What is this sigma bond caused by? That's caused by the overlap of sp2 doing head-on overlap with sp2, and it forms this sigma bond. But we have 2 orbitals left over. There is a leftover p on one carbon and a leftover p on the other. Because it was sp2 hybridization, there's a leftover p. These 2 orbitals can overlap, but notice the overlap is up here and down here. We call that side-to-side overlap. And when you have overlap like that, it is nowhere near as effective at overlapping orbitals as head-on overlap. So the overlap is poorer, and so what you have resulting from p to p orbital overlap is overlap that's above and below the nuclei. So the nuclei are, instead of being attracted to electrons that are attracted to the nuclei, you have nuclei being attracted to electrons up here, and then being attracted to the nuclei here, and nuclei attracted to electrons up here, and then nucleus attraction down to there. And so what you see is that the bond is not direct, and as a result what we have is a weaker bond is called a pi bond. The sigma bond down here is head-on and strong, but the pi bond is weaker. Half of it is below, half of it is above. The strength of the second bond is not a full 1 bond. It is slightly less than that of the sigma bond. So when we look at a double bond, it has the strength not of 2 bonds, but really of about 1.5 to 1.75 bonds. Because this pi bond is weaker, it takes less energy to break. Because it takes less energy to break, when you have it in collisions, it doesn't take anywhere near as much energy to cause the bond to break. And so it is more reactive than a sigma bond. And so this functional group of a carbon-carbon double bond we find undergoes reactions quite easily compared to an alkane. Now, things to know. Because this bond is formed by a sigma bond and a pi bond, and that pi bond is above and below the plane, you cannot have twisting around this double bond. It is planar and it does not twist, because when you twist so that this side is not in the same plane as this side, the p orbitals no longer overlap. So what we have is a planar molecule, very planar. If you would have the hydrogen here, carbon here, hydrogen here, carbon here, hydrogen here, hydrogen here, and all 6 atoms would be in one plane. And because it's sp2 hybridized, you have 120-degree angles all the way around. So it's rigid and trigonal planar. In ethane, you can see this is ethane. Here's carbon, hydrogen, 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 carbon, hydrogen, hydrogen, hydrogen. All you have is a sigma bond. So when I twirl this around out here, the sigma bond is not changed. And so there's no increase with regards to the bond. Now there might be with regards to torsional strain and steric strain, but on a sigma bond, when I rotate it around and around and around, it does not change the energy of the bond in here, the sigma bond between the carbon and the carbon bond. All single bonds are sigma bonds, so all single bonds have the ability to rotate unless they're restrained by a ring. Of course, rings can't have complete rotation because the ring prevents the atoms from rotating around. Okay, so now if we look at this picture right here, you can see carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, sigma bond, and pi bond. This is just going to show you if I go and I rotate this side so that the hydrogen, carbon, hydrogen bonds are at a 90-degree angle to this, that would cause the pi bond to be broken because the p orbital would be at 90-degree angles and there would be no overlap. So rotation does not occur. Only rotation of the whole molecule, stiff as a board, can occur. See how it's rotating as a molecule, stiff, flat. It does not twist around the pi bond.